everyone. Let's start our second round for today. So today, the second round will be Nanjing Daxue team and 成功大学One Angel team. Before we begin our competition, let's first introduce the jury today. So I'm Wen Wenyu from 中原大学 and then this is徐明生老师 from 陆军军官学校 and this is 刘文彪教授 from this 北京师范大学 and 最后是这个刘松芬教授 from 南开大学 and we will have caption. Sorry. We want to have each team introduce your members. Maybe start from Seko.
We're from the team One Angel, and I'm the speaker, Zhang Huanghan. And my members are Gong Huanxuan, Zhu Junwei, Chen Yixing. We're from NCK.
Nanjing Daxue.
Good morning, everyone. I'm Luo Yao from Nanjing University. I'm the captain of the Nanjing University team, and may I introduce my team members to you? 贾秋涵、周国兰、董亮。Thanks for all of your attendance.
Okay, so this round will have each team will have its own topics. So they are going to report different topics. So we will have a slightly different rules. First, we need to decide the team A and team B. So you want to do this猜拳? Yes.
Use everything.
Alright. So we want the team A or team B?
Team A.
We want to be team A. Okay, so 成功 will be team B. 南京大学 will be team A. Okay, so we will have 10 minutes. Sorry. So team A, are you ready? You will begin with the 10 minutes report. And you are ready.
Hello.
Microphone.
Hello everyone. I'm Jia Qiuhan from Nanjing University. The problem I investigate is Azimuthal-Radial pendulum. This is my outline. Let's review the problem. A bulb is suspended from the end of a horizontal elastic rod, and in the resulting pendulum, the radial oscillation, which is parallel to the rod, can spontaneously convert into azimuthal oscillation. To investigate the phenomenon, I did a pre-experiment. I prepared an elastic rod, a stand and a holder, a light rigid spring, and a small ball. Then we can see the device below it. Then we get upward view. Let's see the video. We can see that at first is a radial oscillation, and then it converts into the azimuthal oscillations. Then it converts back into azimuthal oscillation, and the pendulum return. And I have some other findings. First, the conversion happens only when bulb is released in the radial direction. If we release bulb in the azimuthal direction, the oscillation plan doesn't change at all. And secondly, at first is a single pendulum, and it will gradually convert into conical conical oscillation, and then it will convert into single pendulum again. To explain the phenomenon, I built up this theory. Let's see the figure. We use Lagrange to solve this problem. The system is a mechanical system, so we can use this equation. The system has three degrees of freedom, so we can choose the three generalized coordinates x, alpha, and beta. You can see it in this figure. Then we can express the displacement of the ball like the formula 1, 2, 3. Then we get the kinetic energy. This term is the kinetic energy of the ball, and this is the energy of the rod. Also, we get the potential energy. This is the gravitational energy of the ball, and this is the elastic potential energy of the rod. Due to the definition of the Lagrangian. And then we can write down the Lagrange equation 7, 8, 9. Here Q is generalized force. In this system, the generalized force is caused by dissipation. We consider it is proportional to the generalized velocity, and we can write them as this. And we got the dynamic equations that describes the motion of the ball. We can see they are explicitly nonlinear, and the three coordinates are coupling. And this is why the amplitude converges between two directions. We can see this is the simulation result that the mathematics makes. We use the numerical solution to get this result. We can see the motion is very similar to the experiment result. In the theory, we find out these relevant parameters. The first category is initial value of the ball, and the second category is the basic attribute of the system. To get quantitatively investigate, we do the experiments with the high-speed camera. We put it under the device, and we can video the motion of the ball. And then we use tracker to track the trajectory of the motion. The first picture is the data that we traced in the tracker, and we get the locus of the ball in XY plane. If you see clearly, you can see this is not a smooth line, but a broken line that we wire the adjacent data points together. And this one is the simulation result. We can see they are very, very similar. That the structure is similar. That shows this result show a verified theory. And then in the experiment, we find the alpha 0, which is the initial value of alpha, has a great effect on the precession rate. We can see these two pictures. The initial alpha has a difference. The red one is bigger, so it has a faster precession rate. We pick the points when beta reach the maximum. in each period we take points, and we get these blue data points in the figure, and we make we fit them into a straight line, and we get the average rate of alpha. Then we put these three lines into a figure. You can see clearly with a bigger alpha zero, we can get a bigger precision rate, and they are positive rated. And if the alpha zero is extremely small, we can see this video. The precision rate is almost unobservable. And then we change the parameter alpha zero in our simulation program. And we can see with a bigger alpha zero, the precision rate is different. So the theory is again verified by the experiment result. Now we come to the conclusion. First, it's a nonlinear system, and the amplitude transition is caused by the coupling term. And secondly, we found the effect of the alpha zero. A bigger alpha zero can cause a larger precision rate. This is my reference. Thank you.
So we will switch to Team B, present their problem weighing time.
Okay, our topic is weighing time. Basically, we're going to investigate how the weight change as the sand flows. Okay. Okay, this is the outline of our work. We're going to first investigate into the phenomenon description and our model, and equipment, theory, results, and finally conclusion. Okay. So before we go into that, we're going to examine some variables of our experiment. The independent variables are the infill height, the total mass, the texture of the hourglass bottom. The control will be the opening size, the dihedral angle, the texture. And we selected all of these with care. So we're going to explain further when we go through our work. Okay, so these are some basic assumptions of our experiment. So we have a fixed fall height. It impacts the width and the amplitude of the peak. And the total sand weight impacts the fall time. The bottom texture impacts the force exerted on the balance. And we assume that there's no bouncing on sand on collision. And let's go to our experiment model. Okay. So this is the blueprint of a model, and if you want to take a good look at it, you can see it later. Okay, and this is the modeling process, and this is the constraint of our experiment. First of all, we cannot control the size and weight of each sand, and there is collision in the actual flowing process. And the flowing speed variation between trials. It varies trial by trial. And the tension of the switch we use to control the sand. And also, most important of all, the sampling time interval of our mass measurement equipment is limited. Okay, and this is our equipment. We'll have a balance and some sand, an hourglass, water, acrylic, and a switch. There, the paper cap. And next is our theory. So we have a graph that pictures what we're supposed would happen. So for this graph, our assumption is that the flow rate is constant and the sand doesn't bounce. We're going to look at each part of the graph. Okay. So in part one, you see that the reading reduces because that is sand in air. And in the second part, because we assume that the flow rate is constant, so basically the sand in air and the force exerted on sand by sand on the balance cancels. So therefore the reading should remain stable. And as of part 3, we see that as the sand in air gradually reduces and the force exerted from balance to sand is constant. And also the sand fall creates an impulse that makes the force from balance to sand, and therefore the reading builds up. So next, let's go into our results. Okay, so this is our model group with a total sand weight of 300 grams and the fall height to be 45.75 cm. And we're going to go to each part later. Okay, so in part 1A, the initial sand fall, we're going to define some variables that we're going to use later on, like the variable force of sand variable F, the initial weight M0, the sand in air, sand arrive at the bottom, sand bottom, and the mean force from sand exerted to the balance, which is sand min F. And the reading in this part with M0 as the zero reading would be negative sand air. In part 1B, okay, so it would be negative sand air plus sand mean F. Okay, and remember that in our theory we say that it may be stable, but the actual result wasn't a constant, so we need some correction to our null hypothesis. Okay, so the reading higher than predicted in a stable state. So we suppose that the sand doesn't bounce on collision, but in reality it bounces slightly, resulting in an impulse, and it causes the reading to be slightly higher. And also, why is the flow rate not stable during the stable state? So we have the flow rate in 300 grams model, and you can see that there is an oscillation-like tendency of the flow rate. And notice the peaks. That one. Okay, so we propose a model to explain why is that there is an oscillation. So before we have done a model with a 15 dihedral degree, and what happened was, so the D1 falls, the D1 subvolume falls, and the D2, losing support from D1, falls down also, but S stays there. So we converted to another model, a 60 degrees dihedral model, and as you can see, D1 also falls, as there's no support, and D2 proceeds, and D3, D4, D5, all the way to Dn. And basically, that's why it oscillates. It's by process. So why is that? In here, you can see here, there is a downward curve before the final upward curve. It's because that, as you can see, you can see that at about 1.7 seconds, you can see that the flow rate greatly increases. So that results in the rate to dramatically goes down. And this is the equally weighted version of the flow rate, and this is the single data point version of our flow rate. Okay, so part 2, as we mentioned previously, it should be negative sand air plus sand variable F. And as that, the sand variable F is relatively small. The value of it is relatively small. So what is the dominating factor? The sand variable F that substantially increases will be the dominating factor, and it results in a downward curve. Okay. And in part 3, the upper part fall of the sand finishes. So as sand air approaches zero, and also the balance to sand force increases, you can see that it gradually builds up and eventually goes down in the part 3. And next is our independent variables. Okay. Well, then group of high and low, and you can see that in low group, the first peak arrives faster, while the range of the reading very smaller than the experimental group of the high 8. The duration of and amplitude of the last peak is also smaller in the low group. And in this, we compare the total weight of sand. You can see that the first peak's arrival time and amplitude is consistent between the groups. The arrival time of the last peak is shorter for the 200 grams group, while the amplitude is still consistent between the groups. And the next variable we're going to change is the buffer texture. As you can see, the acrylic makes the sand bounces more, so the read is slightly greater in this part. And let's go to our conclusion. So the sand in air reduces the reading, and the sand fallen exerts force on balance, which causes the reading to increase. The variation of the reading is determined by the aforementioned force and the value of sand air. The first peak we see signals the initial sand collision on the bottom. The first pile of sand touches the bottom. And last peak signals the finish of the upper sand fall. And that's the end.
Okay, so now both teams have 2 minutes to prepare your question. Okay, time's up. Now the TP, 成功大学 will ask a question to Team A.
Okay, can you show us your page 4? What is the material and elastic coefficient of the rod? You didn't mention it. The material and elastic coefficient of your rod. Okay. So page 5. Why is that the radial only oscillation not parallel to the rod as stated in the problem?
Because the phenomenon is very clear that if the bulb is released in the azimuthal
Okay, next. On page 14, why is the curve of the motion not complete? Do you finish the curve? The experiment one. And also, why is
at the
it?
same time, the structure of this two motion is are really very similar. The left of the graph is similar as well. But I just want to save time.
Okay, so the duration of your video recorded is duration, time. How much time?
This is the duration of my video is 100 minutes. You can see this picture. This is the duration of my video. It has 10,000 pictures, and this is only a very small part of this video.
Okay.
So the duration is very long.
Okay. So time's up. Now it's for female ask the question.
Okay.
So you're going to ask questions between two people.
First, do you think the flowing rate of sand in the upper part is
Well, no.
will the flowing rate influence the weight you measure?
What point? Which way do you mean? You mean the reading? The reading number on the balance. Do you mean that?
Yes.
So right. Yes, it does.
So, in your experience, have you considered the influence of this?
Well, yes. So that's why we fixed our model.
Let's come to the second. Do you think the point formed in the lower part will impact the weight?
Well, no, because the sub bottom is same.
Do you think the sand still in the air while falling will impact the weight you measure?
Yes. And we propose it in our model.
And then, do you think the shape of the hourglass will affect the weight?
Well, yes. That's why we decided to use this shape.
Then, what do you think the difference between your model and exact the real taxation?
You mean what do I think of
The
real?
model of and the real situation.
Basically, we corrected with the experience, and we proposed a new model that's corrected.
Right, so each team will have 2 minutes to prepare for the discussion. Okay, so we will start the discussion. The first 4 minutes will be the discussion for the teenage problem, Azimuthal-Radial Pendulum. Okay, so we have 4 minutes, so we'll start. Okay, you discuss. Yes. 所以对 pause 一下好了。Let me explain the rule because they are the first one to report. So the discussion follow the question part. It's B team to A team to discuss their problem. Yeah, and then next 4 minutes they will discuss your problem. Okay. No problem with the rules. And then start.
Okay, first of all, the natural frequency of your rod, and also the natural frequency of your string. Do you have any experimental results of the natural frequency of the rod or string?
We have concluded because we have run the Lagrange equation. In this dynamic equation, it has all these measurements. If we have solved this problem, we can solve this equation. We can show the effect of these two parameters in the solution. So where are they? This is because this is related to the mass of the ball and the stiffness of the rods, and so we can get this data from
Okay, I understand. So does the equation include the vibration of the rod?
Yes.
Where?
We can see this equation. The x is the displacement of the rods, and so it's the it has included the vibration of the rod.
Okay. So what radial frequency produces resonance, if there are any? That's the first question.
In the experiment, we find that the influence of the rod is very small to the how we can see.
How do you make sure that the influence is small? Have you tried to change it in your experiment?
In the video, we can see the movement of the arm is according to the motion of the ball. If the ball goes to the right, goes to the left, and the rod's arm goes to the left.
Do you have any
experiment that
supports it? And maybe let's.
We can see in this. You can see the vibration that the rod's arm is the same.
Okay, I see. But most of your experiments are done by the simulation program. Have you actually done the experiment with changing the parameters on an actual experiment, not computational.
Of course, the experiments, the data is from the experiment, but not we produce it.
I mean the alpha
Okay. I think kindly said. Yeah. So the next 4 minutes will be the 18. Okay, and you will section experiment number 16B. Very hard.
First, will geometry that will affect the phenomenon,
Well, yes, that's why we made it symmetric.
and how it will the sun size and the shape of the sun and the size, how will it impact the phenomenon?
Well, it influences how it builds up. How it builds up the sand, how the sand builds up,
So
and also how the sand bounces,
and
and also friction, a little bit of friction.
the question is if the sun is still in the air, should take into account.
Well, no, it's this part. So the sand haven't touched the bottom, so it's a negative read. You see in the first peak.
And should we think the flowing rate of the sun as a constant?
Well, it isn't. We have an experiment graph. It isn't. This is the flow rate of a single data point, and we have an equally weighted version of flow rate. So in our experiment, we found out that it isn't.
How can you measure this flowing rate?
But we did it by dividing dm to dm divided by dt.
Yeah. So let's do data point and we make it.
Yeah.
Yeah. How do you measure it? But now
With a balance. Balance.
but can you take the angle of the repose into account when you analyze your model? This is the angle that the coin has, and this is the maximum angle.
Well, we proposed another model to explain. Oh, wait a minute, not there. We basically explained the phenomenon with another approach. This one. So we divided the fall into several subvolumes and divided into stages. D1, D2, D3, and D4, D5, and all the way to Dn as stages.
Why this is vertical, but not the real situation is slope, but not vertical.
Well, it's because that the sand isn't perfect, as we mentioned in our basic fundamental constraints of our experiment. So, as you can see, so when we lose support here, the D1 falls down. And so this part falls down, right? And losing support, this part falls down and all the way to this. Yeah. All the way to Dn.
So
That's the case of an ideal case, but this is what we observed and proposed.
so you mean the shape of the upper part of the hourglass can change in its growth?
In this fashion, we say yes, but actually it's more stages. It's all the way to Dn. It may be divided into infinite stages. So it's not exactly like that, but that's our model.
So what difference between the more
Okay. So each team will have 3 minutes to prepare for the conclusion. So I remind you that Team B will make a conclusion first. Okay. Okay, so Team B are ready? Okay, start.
2分钟要讲。
Yeah, 2 minutes.
So the opponent is over the team experiment is overly simplified and the constraints and experiment and the model aren't specified enough. It didn't explain it clearly. And the radial only oscillation is not actually parallel to the rod, so that doesn't fit into the problem that you need to investigate. And also, it's highly dependent on the simulation that is in which it is ideal and should not be used to explain the actual phenomenon before you have more experimental results to support it. And you don't have enough experimental data to explain it. And you overlook the resonance and the chaos that's possible to appear in the system. Ours, okay, so the curve of the data isn't simple or stable, which is due to the varying flow rate. And the model is simple but not ideal, but can use to be approximate the actual phenomenon. So you mentioned that we should care about how they build up, but actually in our experiment we didn't see a great tendency about there. So if it builds up that way, it should see a greater tendency to be bigger. So we didn't see that, so we think it isn't significant enough, so we didn't investigate into that. It's too ideal for our condition.
And that's it. That's it.
Okay. Again, you have 2 minutes.
First, I want to say the advantage that first the theory it has a explicit outline and logic, and they use a simplified model to illustrate the physics mechanism, and they modify the theory after finding the difference. And in the experiment, they have the visual phenomena in experiments and observe the tendency of weight change. The shortage is they don't have the specific explain of the inner interaction in the upper part of the hourglass, and there is a difference with the real situation, and in the experiments the data is not so bountiful, and experiment data can't fit your theory. And in my report, I want to say that this picture is not our simulation result, but what we track from the real situation. It's all data points in this picture. And also we find the parameter alpha 0 that imply how it impacts the structure of solution. Okay, thank you.
Okay, now come to the question from the jury. So, that's about
The conclusion.
Yeah. The figure. The picture.
Oh, you mean
The final picture. The final picture. Last one.
this one?
During the discussion, you give a picture. I mean, okay. You have a picture of the
200 grams.
yeah. The last period you have yes this one.
This one. Oh,
Yeah. The last period you have bigger big number than original big. How to explain the phenomenon?
Oh, you mean
Yeah.
that one? Why
Please
is
give me some explanation of this.
this one?
Yeah.
We think it's like almost the same.
The just the final
Together from here and here, we think it's about the same.
the last one, the last top.
You mean this one?
The last one. Yes.
This one?
Yes.
You mean the width of it?
Yeah. Give me some explanation of this phenomenon.
We think you can. There's another way that you can from here. This because this and this is the same problem.
I mean,
Are you talking about the width or
why we can access the width is bigger than the original width in the last period.
Oh, you ask why?
Yes.
Okay. So it's because that the upper part already finished falling. So in this part, the sand fallen from the upper part built up. And when they all build up, it's like here and eventually goes down. 这看有什么问题？
You're satisfied? Okay. Some more questions? Okay,
I have
you're
a
last.
question for that you mentioned the small alpha, medium alpha, and the large alpha. Yeah. Okay. So, can you give me the different conditions for these three cases?
It's the angle between the vertical direction and the initial position of the ball. It's the wheel see from the end of the device, and it's the motion in XY plane. So alpha zero is like the definition in our model. This is the alpha zero.
Which alpha is the initial alpha or initial alpha?
We can see in the picture. This is the release phase of the ball.
Okay, I have for Team B. Yes. What's your basic theory about your model?
You mean the theory of how the weight varies?
Yeah.
Yeah. we suppose that in the first
I
part,
guess, yeah, what you show is the assumptions. I ask you the basic theory.
It's just an okay. So the first part, the reading from balance reduces because there's sand in air and it hasn't touched the bottom yet. So when it touches, the reed builds up. And the next part, we suppose that the flow rate is constant. So we think that it will be a stable state. It's a line in our theory. Okay. And as a third part, so the sand in air gradually reduces as it hits the bottom. The above counterpart already has no sand. And the sand falling from the upper part crashes on the balance and causes impulse and builds up a reed.
So what you mean? You all theory as Newton's law?
What?
I mean that you used a Newton's law.
What kind of laws are these?
Newton's second law.
Impulse.
And maybe I have a question following Professor Liu that you show the theory slide. You only have this curve. So I think Professor Liu is trying to ask you, how do you get this kind of curve under that assumption? Even without assumption, what kind of, for example, formula or how do you predict that shape is like this? How do you get this curve? You have some description.
Basically, we first observe some experiments without seeing the exact graph, and we think that it has this tendency, and we formulate as this. And we try to explain it by making some assumptions and also results.
Any more questions? Maybe I have a last question for Q&A. So you talk about the very different initial alpha. Did you have tried to change the beta and also x in your parameters?
First, we think they can be described by the equation. But I want to on the next step we try to get an analytical solution and directly get the connection between the parameter and the result, and we think we can make a better device to change this parameter and make a better report.
So you're saying you haven't done the experiment for changing beta or changing x?
We have changed this parameter, but we didn't find a clear.
Okay. So you see there are some effects from the experiment.
Yes, because the.
But you should show also in your experiment.
Yes.
Yeah, even you don't have a theory yet.
Yes.
Any more further comments? So maybe we take a few moments to break. So we will have first grade for Team A, 南京大学. Right? So we have 7. Please raise the score. Maybe from there. 7, 7, 7, 8. Then we will have a score for Team B, 成功大学. So from there, we have 6, 8, 6, 7. Attention for everyone and all the participants. So we conclude our today's competition.